Hello. So this problem, we're aiming to take a derivative of this sort of monster equation here, right? So this is sort of a classic sort of example of a sort of situation you might run into, because this thing, right, is really a polynomial, but it's in factored form, which is sort of the ideal way to have a polynomial, right? So it's sort of not uncommon you might run into that kind of form. And yet, if you want to take a derivative of this thing, what are you going to do? Like, what is that, the quintuple product rule? Like, that's madness. Who would want to do that, right? So, sort of, in the words of Nemo, there's got to be a better way, right? The starfish, there we go, Finding Nemo. Maybe a dated reference, depending on when you watch this video. So, nonetheless, in fact, there is a better way, right? So, what we're going to do is we're just going to sort of cheat a little, which is to say we're going to be sort of suitably clever. So the idea here is that we want to break up products, because products are annoying for derivatives, and really we wish it was sort of some sort of sum. And it turns out we know a way of doing that, right? So in particular, if we sort of recall our sort of handy-dandy log rules, right? We have log of a times b is log of a plus log of b. So really, we kind of really wish that this whole big equation thing was really log of that whole big equation thing, right? Because if it were a log, then I could split it up nicely. And we could lament that, it doesn't have a log, or we could introduce a log. And in fact, that's what we're going to do. So instead of having sort of f of x, what I'm going to do is write it as y, right? So I'm going to have y equals, and then this whole thing, so I'm going to have x times x plus 1 times x minus 3 times x plus 7 times x minus 6. So seems like my marker is drying up a little here on me. There we go. Okay, now if you notice I left some room that was, not so subtly on purpose. Whew, talking, right? So what I'm going to do is I'm going to introduce a log by taking a log of both sides, right? So I'm going to say, okay, I'm going to take the log of that side and the log of that side, okay? And then I'm going to use my log rules to split this up. Now you may wonder, can I do that? Because I want to find my derivative, right? I want to find y prime, or dy dx, and now I've introduced a log on the y. And the short answer is yes, I can do that, because I'm crazy. No, because as long as I do the same thing to both sides, this is still mathematically valid. But the sort of concern is valid too, in that I want to make sure that I can still get dy dx at the end. And the answer is I can, but I'm going to be able to do it because I'm going to need to use implicit differentiation. So that's going to come up as well. So I'm sort of looking forward a second. First, I'm going to use my log rules to break up this monstrosity though. So here, I'm going to basically every product here becomes a sum. So I'm going to have natural log of x plus natural log of x plus 1 plus natural log of x minus 3 plus natural log of x plus 7 plus natural log of x minus 6. There we go. Okay, so now I can take the derivative of both sides, but I, again, have to be careful because the derivative on the left is no longer simply dy dx, right? Because the derivative on the left is, right, a natural log of y. If I take the derivative of that, well, natural log of stuff gives me 1 over that stuff. But because it's y and not an x, and I'm taking a derivative with respect to x, then I have the chain rule, right, implicit, telling me that I should have also dy dx. Okay, so that's what happens on the left, right? The natural log gives me 1 over that thing times the derivative of that thing, which is dy dx. But on this side, when I take the derivative of x each way, like all across, well, derivative here, right, is just 1 over x. Here, I'm going to get 1 over x plus 1. And then by the chain rule, I'm going to multiply by the derivative of x plus 1. But the derivative of x plus 1 is 1. So I don't have to worry about that, right? Because the derivative of x is 1, derivative of 1 is 0. So there is a chain rule happening, but it doesn't do anything. So I'm going to not worry about it. Same deal here. I'm going to get 1 over x minus 3. But again, I have a chain rule, but the derivative of x is 1, derivative of 3 is 0, so I'm multiplying by 1. Maybe just to be clear that I've sort of thought about it at least, I'm going to write in the fact that I'm multiplying by 1 here. You don't need to do this in your work, but I want to make it clear that like there was a chain rule. I had to address the chain rule, but the chain rule turns out to just be multiplying by 1, so it's okay. There's not like anything spectacular happening. Here, 1 over x plus 7 times the derivative of x plus 7, which, again, in this case, it's just 1. And here, 1 over x minus 6. And derivative of x minus 6, again, is 1. This does happen a lot with logs, that it turns out the chain rule is just 1, but not always. So you really do have to keep track, because that will not always be the case. Sometimes you will actually need some other number there. Okay. Now what? Well, here, so backing up a second, I did an implicit differentiation, right? And part of that process is always, and then we solve for dy dx, right? So we have to get dy dx by itself. So in particular, the only dy dx is here. There's none on this side. So I've already sort of got it in the form of all the y prime stuff on one side, all the non-y prime stuff on the other side. So, excuse me. So I'm just going to isolate that. So I'm going to multiply by y. So that gets me dy dx on this side equals all of this stuff. So that's 1 over x plus 1 over x plus 1 plus 1 over x minus 3 plus 1 over x plus 7 plus 1 over x minus 6 times y. Now, you may want to think that we're done, but we're not. So before, when we did implicit differentiation, it wasn't unusual to have a function at the end, right? Your dy dx you could always solve for, but the resulting thing may or may not be implicitly defined, and that's pretty normal because our original function was implicitly defined. But if we remember, our original function was not implicitly defined, right? It was explicitly defined. It was only x's. So that should be the thing we give back, right? We don't want to give back an implicitly defined thing because that's just really not cool, right? Be like, you gave me a relatively nice form and I'm giving you this totally incomprehensible crap back to, deal with. Don't want to do that. So we want to be able then to get rid of y. We want to have just x stuff over here. How will we do that? Well, it turns out we can get rid of y because we know what y is. In particular, y is this big mess, right? So I'm going to substitute that y. So in particular then, I get dy dx equals this thing, 1 over x, 1 over x plus 1, 1 over x minus 3, 1 over x plus 7, 1 over x minus 6, all of that stuff still, times what y was, which was sort of all the stuff inside the natural log, or all the stuff sort of up here, right? So that's the x times x plus 1 times x minus 3 times x plus 7 times x minus 6. Now this is indeed my final answer. Now this sort of shows the power and the trade-off of logarithmic differentiation, right? Because on the one hand, excuse me, got the yawns. I've been doing this a lot. So on the one hand, the sort of derivative step was pretty painless, really. Like once we had actually separated out, taking the derivative was quite straightforward, right? It's just 1 over stuff and then maybe some chain rules that in this case didn't end up doing much, but maybe you had to keep track of them. But the sort of trade-off for the nice derivative step is that this thing is no longer in a particularly nice form, right? So this format is not nearly as nice as the original sort of factored form. And in some sense that was sort of inevitable, because the only other way we could have done this was a whole lot of product rules or expanding this all out and then taking a derivative, either one of which was not going to result in a factored form. But neither of those was going to have a bunch of fractions either. So like there is a trade-off, right? The end result is not nearly as nice as the other form as it sort of could have been, okay? So really it comes down to what you're trying to accomplish as to which of these might be better or which approach might be better. But from a just taking a derivative standpoint, this is vastly easier. So this is a very useful tool to sort of have in your pocket, okay? So that is that. Hello. So in this example, we're taking a derivative of some real monster of a thing. So we have here a triple product. If we sort of look carefully, right, we have the x plus 1, and then this whole thing is actually one thing, natural log of x squared plus 1, all minus 4, and then e to the x squared. So there's sort of a bunch of ways that we could do this. We could do a triple product rule. We can multiply all this out and then have sort of individual stuff, although the fact that there's a bunch of different functions like an e, a natural log, and a regular x means that we probably still have triple rules in there, so that's probably not any better. But another way we could do this, and the way we're going to sort of give this a shot, is by using logarithmic differentiation. So the first thing I'm going to do, right, if I think of f of x as y, I'm going to take natural log of both sides. So natural log of y equals natural log of, so then I'm going to have e to the x squared times natural log of x squared plus 1, all minus 4, and then x plus 1. Now, I'm doing this because I want to use the fact that log of AB is log of A plus log of B, right? I want to use the fact that I can split up my log rules. So my first step is going to be that, right? So I'm going to take this, I'm going to say, okay, I got natural log of e to the x squared plus natural log of x squared plus 1 minus 4 plus natural log of x plus 1. But remember, I can't do anything about log of a plus b, right? It's only if they're having a product, so I can't split this thing up, unfortunately. So this really is about the best I can do splitting it up-wise. But I can do a little bit more, especially right here, right? So I can rewrite this by using the power, right? Because another rule we have is log of a to the b is b log a, right? So in particular, I could take this x squared down, and then I have x squared times natural log of e, and natural log of e is just 1. Or I could think of this as natural log is asking e to what power is e to the x squared, which means either way, I'm going to get x squared here. So that actually sort of simplifies pretty nicely. Unfortunately, it's kind of the only thing that simplifies nicely out of this mess. The rest of it is just the same. Okay. So now I can do my derivative step. Now my derivative step is going to get a little iffy in here because I'm going to have some crazy chain rule nonsense happening, but that's life. So on the left, I take the derivative of natural log of y. So the derivative of that is 1 over y times the derivative of y with respect to x, so dy dx. Here, I'm taking the derivative with respect to x. So the derivative with respect to x of x squared is just 2x, right? Drop the 2 down, subtract 1, 2x. Now, the derivative here, right, and again, as a sort of reminder, if I take the derivative with respect to x of some natural log of, let's say, u, some non-x thing or some function of x or something, this is 1 over that thing times the derivative of that thing. So in particular, here I have natural log of a bunch of stuff, so I'm going to get 1 over all of that stuff, natural log of x squared plus 1 minus 4 times, by the chain rule, the derivative with respect to x of that stuff, right, of the natural log of x squared plus 1 minus 4. Again, to be clear, all of this is the chain rule. And then I'm going to have plus 1 over x plus 1. And then same deal here. I have to take the derivative of x plus 1, but that's just 1, right? So this is also chain rule. Okay. But I still have stuff to do, right? I'm not done with the derivative step, so I'm going to keep going. So that's still 2x plus still 1 over that behemoth, natural log of x squared plus 1 minus 4 times. So now I need the derivative of this thing. Well, it's another derivative of natural log, right? Just like we were talking about over there. So this is 1 over that stuff, 1 over x squared plus 1 times, and then the derivative of that stuff. Derivative with respect to x of x squared plus 1. So to be clear, all of this is the chain rule. So that was this first piece, right? The natural log was 1 over that thing times the derivative of that thing minus derivative of 0 of so minus derivative of 4, which is just 0. Okay, and then that stays the same. And I'm still not done, right? Because I still have this thing. So this is still 2x plus 1 over natural log of x squared plus 1 minus 4 times 1 over x squared plus 1 times derivative of x squared is 2x. Derivative of 1 is 0, so I just have 2x there, plus 1 over x plus 1. Okay? So this is my derivative step. But again, I'm not done, right? Because I'm doing implicit differentiation, so in particular I need to isolate my dy dx. So my dy dx then is this side, right? Because I'm basically going to multiply by y to get it over on this side. So I'm going to have 2x plus 1 over. So I could put all these together. Maybe I will in this case. So if I multiply, here, let me do this. Multiply all 3 of these terms together, I'm going to get 1 times 2x. I'm going to get a 2x on the top over, and then I'm going to get, so I guess I'll write this one first, x squared plus 1 times natural log of x squared plus 1 minus 4. Okay. All plus 1 over x plus 1. So I have all of that stuff times y, because I have to move the y over. And again, one of the things with logarithmic differentiation, right, is the original thing was not implicitly defined. It was explicitly defined, which means I should give back an explicitly defined function. In particular, I need to get rid of this y by subbing out with what y is, the original function, right? So I have 2x plus 2x over x squared plus 1 natural log of x squared plus 1 minus 4 plus, I'm writing it a little smaller because I have a lot to write here, plus 1 over x plus 1 times, and then what y is actually equal to, which was e to the x squared times natural log of x squared plus 1 all minus 4 times x plus 1. So this is an example, right, as we notice here several times, where the chain rule was key, right? If we just sort of always assume that when we use logarithmic differentiation that the chain rule won't matter, you can go horribly astray, right? So we really want to make sure we keep track of the chain rule. Nonetheless, this is then my final answer. And again, as a sort of worthwhile note, right, the derivative step wasn't great, but it was still a lot better than the madness that would have been trying to do this directly. But the trade-off is that this form is pretty awful, right? Like that's a pretty ugly, that's a pretty ugly function. Imagine trying to take a derivative of that thing again. Oof, that would be awful. So nonetheless, this is sort of the nice way of getting the derivative, even if the derivative form isn't as nice as if we had done it maybe directly. Okay, so that's that.